In this example, we want to identify an exception to the isolating the radical rule that could be beneficial when it comes to solving a radical equation. If we really wanted to isolate the radical for this example, we would have to begin by subtracting 4 and then dividing by 2. You can already see how that would become problematic. Having to subtract the 4 wouldn't be bad, but then dividing by 2 would create an x over 2 that would then have to be squared and attempted to be solved with. So we have the option, should there be a coefficient in front of the radical, to just leave it there. And our second line is going to read 2 root x plus 6 equals x plus 6. And it's from right here that we're going to square both sides of this equation. On the right-hand side, we have a simple squaring of a binomial, x squared plus 12x plus 36. But on the left-hand side, we're imagining 2 root x plus 6 times 2 root x plus 6. In that case, the 2 times the 2 becomes a 4, and the root x plus 6 times the root x plus 6 just becomes regular x plus 6 with no more radical. Leaving that 2 in front of the radical gave us the advantage of having only constant integer coefficients instead of moving that 2 over to here and then trying to square something, creating fractions that we don't need and extra work for us. Because we have a quadratic equation that we're going to solve here, we're going to move everybody over to the right-hand side, set this equation equal to 0. If we subtract 4x from both sides, we're left with 8x. And if we subtract the 24 from both sides, we're left with 12. Factoring that polynomial, we get x plus 6 and x plus 2, leaving us with our two solutions, x equals negative 6 and x equals negative 2. As in any situation with radical equations where we had to square to potentially create an extra extraneous solution, we're going to check both of our solutions to make sure that they are actually valid in the original equation. So we'll start by checking negative 6. So negative 6 goes in the place of x in both spots. This just becomes 0, leaving us with 4, and negative 6 plus 10 is 4, so negative 6 is good. Now we'll check negative 2. Negative 2 plus 6 plus 4 equals negative 2 plus 10. This side is just 8, so we're looking for the left-hand side to also equal 8. This would make a 4. The square root of 4 is equal to 2. 2 times 2 is 4, plus another 4 is 8. And that one checks as well. So we have this extra consideration at this point, thinking through this last example, of what to do when there's this constant multiple here. If it divides nicely into the terms on the other side, then divide it, get it out of the way, and take care of it. But if it doesn't, it might make sense to leave it on the left-hand side like we did here as part of the square so that it can be handled as an integer coefficient and not create more work for us by creating a fractional coefficient.